Like most engineering departments at Apple, we'd be lost without computer-aided design. It helps us visualize our wildest ideas, explore the integrity of engineering concepts, or simply put finishing touches on a set of drawings. Our job in product design is to create solutions that are sophisticated yet appropriate, ingenious yet easy to manufacture. Our staff is constantly searching for new ways to solve old problems. We're a bunch of hard-working, dedicated professionals who love to push the envelope on technology. This is an exact model of the Macintosh IIcx we painstakingly designed on screen. It's our first chance to see our ideas in action. We pore over the details, checking every clearance, every fit, every dimension. When you're manufacturing thousands of products per day, it pays to sweat the details. Here's one of our designers using a fluid dynamics program that we've ported to Apple's Cray. This enables us to simulate molding plastic parts before we actually build the tool. A few years back, we had no choice but to build a tool and then refine it by trial and error. Now with this new advanced simulation capability, we can quickly and thoroughly validate our designs early in the development cycle. In the tool, plastic has the consistency of taffy flowing on a warm day, yet it's a complex hydrocarbon chain. Bruise the material through rough handling and you're likely to lose the material properties, structural integrity, or end up with parts that look like our competitors. Here, for example, we're simulating molten plastic flowing between steel plates that are laced with obstructions. To do this, we use a mesh generator to form a finite element grid on the surface of the part. In essence, what we're doing is breaking down an extremely difficult problem into thousands of more manageable simultaneous equations. 24,000 unknowns were turned over to the Cray. We reached a solution within 1.5 hours, whereas before we used a VAX, and it took 7 days. From the data on the screen, we can now zero in on important performance parameters of the mold, such as material temperature, pressure, and flow. This information tells us how we can then adjust the design of the part or mold to allow us to build the best products that are both rich in aesthetics and high in engineering integrity. Now let's leave the pristine environment of CAD and visit our tool construction shop, where the chips are flying. It takes more than $200,000 and 6 months to transform this block of steel into a precision production tool. Before it leaves this shop, the tool will be handled by dozens of highly skilled tool makers and their machines. From numerical control mills that are fed detailed surfacing information from CAD files, to EDM, which uses electricity to carve out cavities in steel, removing metal one particle at a time. The process uses carbon electrodes and up to 80 amps to burn away unwanted steel. At the rate of 1,000th of an inch per minute, it's a slow, exacting process. Our finishing touch is the human touch. We fit and polish all completed components by hand, rubbing out each machining part with the old-fashioned method of abrasives and elbow grease. It's a time-consuming process, but sometimes the old ways are still the best. Finally, we have a precision instrument measuring 3 feet on a side, weighing 10,000 pounds, and made to tolerances 1/3 the diameter of a human hair. After 10 months of hard work, we're now ready for the final test at the plastics molding shop. Here we use little beads of plastic that start off the process in this big blue hopper. Then the beads enter the tube where they're melted and finally injected into this monster of a molding press. Inside the machine is the mold mounted on steel plates called platens. With physical conditions more like those on Venus, 1,700 pounds per square inch and 400 degrees Fahrenheit, the forces developed in the mold are extreme. To counter them, the press exerts up to 1.5 million pounds of force on the platens. and these keep the mold from blowing open. It takes less than 2 minutes to mold a part this size. Recognize it? It's the bottom half of a IIcx housing. Now watch this delicate maneuver as the platens separate and 14 pieces of steel move in a carefully prescribed sequence to free the molded part from the tool. The part is checked for quality and then packed for shipment to the factory. We repeat this cycle thousands of times a day, millions of times a year on 3 continents. You've already seen the heart and soul of our operation. Now let's see where silicon, metal, and plastic all come together at our Fremont, California plant, located just a few miles from the molder. Parts like the IIcx housing arrive every hour and are delivered directly to the IIcx production line. We pride ourselves in using advanced manufacturing technology to minimize the number of people and floor space needed for final assembly, and to keep production moving at a healthy clip. You'll find the robots on this advanced manufacturing line look a lot like people. Here's where sweating the details in the design, tooling, and molding phases really pays off. IIcx assembly is so easy, most anyone can put it together flawlessly.